Hi everyone, in this video I'm going to show you how to calculate the electric field of an extended body. Let's jump right into it. So an extended body is an object that is composed of infinitely many point particles. So the electric field of a point particle, of one in particular, say we have a charge q located in space at x prime, y prime, z prime. If we want to know what the electric field is at another point, say at x, y, z, Coulomb's law tells us that that the electric field at x, y, z is in SI units 1 over 4 pi epsilon 0 times the charge over the distance between the points squared. So I'm calling the distance a script r. That is the distance from xyz to x prime, y prime, z prime. Now the electric field is a vector, so I need to also put r hat. That is the unit vector that points from q to the location that we want to know the electric field. So for this example here, the unit vector is we subtract the x components. We start with the 2 vector and we subtract the x component of the from vector. So it's going to so the x component is x minus x prime. The y component, we subtract the 2 vector from so it's going to be y minus y prime and then z minus z prime. Always 2 minus from. And because it's a unit vector, I have to divide by the magnitude. So square root, and then the x component squared, and now plus the y component squared, and then plus the z component squared. So this is just for a single particle, a single charge. And if we have multiple charges, say we have Q1, Q2, and Q3, and we want to know what the electric field is over here, then what we do is we have to add the electric fields from each of these individual charges here. So the total electric field is going to be the vector sum of E1 plus E2 plus E3. These are the electric fields from these individual charges here. So again, the total electric field is the resultant vector of this sum. So if we have an extended body, say we have this shape right here, what we do is we label a particular point, x, y, x prime, y prime, z prime, and say we want to know the electric field at this point in space, x, y, z. What we do is we look at the electric field of this particular point. So we take the it's going to be pretty much the same, but we look at the differential of the electric field. So this is going to be 1 over 4 pi epsilon 0 times dq over r squared r hat. Now, this tells us, so this equation here is the electric field due to a single infinitesimal portion of charge on that extended body at the point. And to obtain the total electric field, E, we have to integrate dE. Now, what the integral does is it automatically it automates the process of adding the individual vectors from each point in this body. So I'm going to bring the constant out in front. So this is 1 over 4 pi epsilon 0 times the integral of dq over r squared r hat. Now you may find this strange that that this is an integral over dq. Back in calculus, we evaluated integrals, say like x squared dx. We never. It's weird to have dq and r. So as it is, this integral cannot be manipulated because q is a physical quantity. It is a charge. It's what you can measure. Whereas the integrals that we're used to from calculus, x is a geometrical quantity. It is a distance in space. So what we have to do is write dq in terms of in terms of geometrical quantities, and we do that by using density, charge density in this context. So in one dimension, we use a linear charge density, lambda, and multiply that by a differential of arc length ds. ds in this case, so this is for one dimension. ds is arc length, and we divide it by r squared and then multiply it by r hat. And in two dimensions, we use a surface charge density, which is sigma. It is, in general, a double integral because now we're in two dimensions. So this is going to be sigma at the location x prime, y prime, z prime, dA over r squared times the position, the unit vector r hat. So this is for two dimensions. And in three dimensions, we use a volumetric charge distribution. That is, the typical symbol for that is rho. And we multiply it by volume differential over r squared and then r hat for 3D. So again, the total is, so these formulas here are they add up the electric field from each of the individual particles that the extended body is made of. So in general, you won't have to do double and triple integrals. That's just for a general body. What you see in physics classes are symmetrical bodies, and when the shape and the charge distribution are symmetrical about an axis, you can get away with only with doing a single integral. So it is much. It's not as messy as it looks. These are just general formulas for the general case. I'll probably do some follow-up videos and show you how to calculate the electric fields for some simple objects to demonstrate how to calculate the electric field. All right, thanks for watching. So actually, before I end this, I just want to say that this should be ds prime, and also these integrals are taken over the charged body. So this is over a curve in space. This is over a two-dimensional surface S, and the triple integral is over a three-dimensional charged body V. All right, that's the end.